Hello, good morning, sir. My name is Alan. I'm from second year EC department, and today I'm going to give a presentation about the topic Verilog design of latches and flip-flops, a practical guide. Verilog design of latches and flip-flops, a practical guide. This guide will explore the design of fundamental memory elements like latches and flip-flops using the Verilog hardware description language (HDL). We will dwell into the basic building blocks of digital circuits, covering their structure, behavior, and implementation. Introduction to Verilog and Digital Design Fundamentals. Verilog HDL, a hardware description language (HDL), is used to model and design digital circuits. The next thing is Digital Design Fundamentals. Basic concepts of Boolean algebra, logic gates, and combinational or sequential circuits. Verilog Basics. Data types, operators, modules, and behavioral or structural modeling. Synthesis and simulation. Transforming Verilog code into hardware and testing the design functionality. Basics of Verilog. Data types. There are different data types like wire, register, integer, and other data types used to represent signals and variables. Operators. Logical, arithmetic, bitwise operators for manipulating data. Modules. Encapsulation of logic to create reusable components. Latches and flip-flop basics. Latches. Level sensitive memory elements that store a value as long as the enable signal is active. Flip-flops. Edge triggering memory elements that store a value at the rising or falling edge of a clock signal. Coming to the next slide, SR latch design. SR latch, a basic latch with set S and a reset R inputs. NOR gates, implementation using NOR gates. We can see it here. And the truth table. We got set, reset, Q is which is output, and Q bar which is a complement. So the inputs are 0 0, then output is no change, complement is no change. So the input is 0 1, output is 0, and complement is 1. Input is 1 0, output is 1, complement is 0. The input is 1 1, and the output is undefined, the complement is also undefined. Coming to the next slide, D latch design. D latch, a latch with a single data D input and an enable signal. Data transparency. The latch follows the input data when the enable signal is high. Latching data. The latch holds the last data value when the enable signal goes low. Coming to the next slide, D flip-flop design. There are two types in D flip-flop design. They are positive edge triggered and negative edge triggered. In positive edge triggered, the D flip-flop design the D flip-flop changes its state at the rising edge of the clock signal. Negative edge triggered, the D flip-flop changes state at the falling edge of the clock signal. The next thing is JK flip-flop design. Toggles. The output changes states at each clock edge when J and K are high. Sets. The output is set to high when J is high and K is low. Resets. The output is set to low when J is low and K is high. Holds. The output stays the same when J and K are both low. Coming to the next slide, T flip-flop design. T flip-flop. A T flip-flop that toggles its state changes to the opposite value at each clock edge. Toggle behavior. The T input determines the toggle behavior of the flip-flop. We got the truth table. When T is 0, there is no change, and when T is 1, it toggles the output. Toggle behavior. Counter frequency dividers. Coming to the next slide, edge triggered versus level triggered. Edge triggered activates on a clock edge, positive or negative. Common in flip-flops like D flip-flop. Advantages: more precise timing control, changes states only at the clock edge. The next thing is level triggered. Responds to a level of the clock, high or low. Common in latches like D latch. Advantage and the advantages are simpler design but sensitive to input changes throughout the level. Introduction to latches and flip-flops. Basic building blocks. Latches and flip-flops are basic building blocks in digital circuits serving as memory elements. Data storage. These elements hold and retain information, allowing circuits to store and process data over time. Sequential logic. They are integral to implementing sequential logic, which depends on the order and timing of signals. Understanding latches. SR latch, gated latch, transparent latch. Coming to the SR latch, it's the simplest type of latch controlled by set and reset inputs. Coming to the gated latch, a gated latch is controlled by an additional enable signal enabling data flow. Next thing is transparent latch. It's a latch that directly follows. The next thing is transparent latch. A latch that directly flows the input signal when enabled like a transparent window. It's called transparent latch. Coming to the next slide, flip-flops. Edge triggered memory. D flip-flops. A latch triggered on the edge of a clock signal, storing data only on the rising or falling edge. JK flip-flop offers versatility with inputs J and K, enabling various functionalities like toggle and reset. T flip-flop, a simplified version of for toggling the output state with each clock pulse, ideal for counting applications. Verilog implementation of latches and flip-flops. Module definition. Define a Verilog module to encapsulate the latch or flip-flops behavior and connections. Input and output ports. Specify input signals like clock, data, and reset, as well as the output signal. Logic implementation. Use logic gates and behavioral statements within the module to define the latch's operation. Coming to the next slide, design considerations. The following are the design considerations. They are clock frequency, setup and hold times, asynchronous inputs. Clock frequency. The clock frequency determines the maximum data rate the flip-flop can handle. Setup and hold times. Ensure proper timing relationship between the data input and the clock edge for reliable operation. Asynchronous inputs. Handle inputs that are not synchronized with the clock signal to avoid race conditions. Applications of latches and flip-flops. They are counters, memories, registers, and shift registers. Coming to the counters, flip-flops are used to create counters that track and increment a digital value. Coming to the memory, latches and flip-flops are fundamental components of RAM and other memory systems. Registers. They form registers for storing and manipulating data within the digital circuits. Shift registers. They are used in digital transmission, storage, and processing applications. The next slide is practical examples and case studies. Examples. The examples are digital clock, traffic light controller, digital audio player. Coming to the digital clock, flip-flops are used to count time and update the display with seconds, minutes, and hours. Coming to the next example, traffic light controller. They manage the sequence of traffic signals using counters and timers. Coming to the next example, digital audio player. Shift registers are employed for processing and playing back audio data. Coming to a conclusion, latches and flip-flops are fundamental components of digital circuit design, providing essential memory capabilities and enabling the realization of complex sequential logic. And that's it. Thank you.